Hello and welcome to Module 57, Toxicology and Chemical Risks. So harmful chemicals are grouped into 5 main categories, and they're listed here. So we've got neurotoxins, carcinogens, teratogens, allergens, and endocrine disruptors. So we'll talk about each one. So neurotoxins basically disrupt your nervous system. So think of nervous system, neuro. So insects are affected by insecticides. So they make them not be able to fly. They make them not be able to function. They can't breathe, and they generally die in that case. And then humans are affected by lead and mercury. So some examples of neurotoxins for humans: lead and mercury, which we both talked about in the environment. Carcinogens cause cancer. So think of both of them start with C. So carcinogen, cancer. So examples of carcinogens for humans: asbestos, radon, formaldehyde, and the chemicals that they put into tobacco for smoking. And so a mutagen causes genetic damage. So carcinogen just causes cancer to your body, but a mutagen causes genetic material to be damaged, and therefore you can pass that on to children. So that would be obviously a really bad thing. And then teratogens, they interfere with the normal development of an embryo or fetus. So some examples: in the 70s, sometimes women were given thalidomide, and that was to prevent morning sickness. And so we later found out that that caused damage to the fetus. And so there was development was not normal. So sometimes people were born without hands or partial limbs, things like that. So it damaged the development of the fetus. And then there's alcohol syndrome. So fetal alcohol syndrome is from drinking alcohol, usually an excessive amount of alcohol during pregnancy, and so that can cause damage to the fetus, their brain. It causes a lot of damage to their development in the embryo or in the womb. All right, so allergens are not necessarily deadly. They can be. So if you have a peanut allergy and you're exposed to peanuts, that could be very deadly. But we've got allergens like pollen and things like that. So those aren't generally deadly. But we can get, milk or peanut or shellfish allergies as well. And then some common allergens to medicine: penicillin. So it's a type of antibiotic, but penicillin is a very common allergen. And then codeine, which is just a treatment for pain. So those can cause allergic reactions. And then endocrine disruptor just basically means that it affects your hormones. So your endocrine system is where your hormones are made and spread throughout your body. So some examples of endocrine disruptors: it's our medicine basically that gets into the environment. So there's really not any waterway in the world that doesn't contain some form of human medicine, which is kind of sad. But really common things would be birth control pills. So maybe they're thrown away, they get into the waterways, things like that. And so pesticides, those can also run off into the waterways. And so they have things in them. Well, obviously the birth control, but pesticides as well have things that mimic our hormones, and they mimic estrogen. And so what it does in the environment is it causes amphibians, and mostly amphibians, but it causes some fish also to not be able to reproduce. So they have low testosterone levels because there's estrogen in the waterways, and so it causes them to not be able to reproduce as well. It also causes them to develop into more female versus male bodies, and so that affects their reproduction. And that happens quite often. So like I said, there's no waterway in the world that isn't affected by some type of endocrine disruptor. All right, so we look at these different substances in the human body, and we figure out what would be a certain dose that would be lethal. So we've got a couple different terms up here. LD50 stands for lethal dose that kills 50%. So that's considered lethal once it kills 50%. And then we've got effective dose. So that's what ED stands for. So that would be giving medicine. So what is the effective dose? So when they decide you get one Advil, or something per person, they're looking at the average weight of a person, And then they're looking at what's the effective dose that 50% of humans will respond to, or 50% of rats, or whatever they're testing. But so that would be effective dose. So lethal dose would be killing you. Effective dose would be effective, like helping you. And then there's two different studies that we can do. There's chronic, so that would be over a long period of time. And then acute would be short period. And so acute, we're talking like maybe 1 to 4 days. Long-term chronic studies might be a year, maybe longer. Just depends on what we're studying. And then if you look at the graph over here on the left, it shows dose response. So basically right here would be 50%. So this is the subject. So at 50%, this would either be the effective dose or the lethal dose. It depends on what we're looking at, what kind of dose that we're looking at. So then they would figure out what is that per body weight, so that we can figure out what would be toxic to a human or to whatever organism we're looking at. And then this NOEL, it just means no observed effect. So right here, there's nothing. We don't see any observed effect. There's 0%. And then we start to see a steady incline. And so at 50% is where we have the ED or LD. And then this would be, if we're looking at lethal dose, this would be 100% death. Or this would be 100% effective for everyone. All right, so the testing standards. So there's a couple different things that regulate testing. So EPA is Environmental Protection Agency. That's really important, especially for environmental science. But the Federal Insecticide, Fungicide, and Rodenticide Act of 1996 basically is just regulating manufacturers of different things. So things that kill rodents, fungi, insects. And then we want to know, does that like affect the environment? So they need to demonstrate that it does not affect the environment unreasonably. So of course there's going to be some effect on the environment, but is it detrimental? Is it going to affect lots of different things, and is it going to be really bad? So there is regulation on, they need to prove that it's not going to just annihilate everything. And then for testing, what we use for humans is our mammals, not just humans, but mammals, are mice and rats. And so the reason that we use that is, one, it's unethical to test on humans, but mice and rats are very similar. They're mammals. They're very similar. They have a very short lifespan and high reproductive rate. And so that makes them really ideal because we can test lots of different generations very quickly and see what's happening. If we use something else, it might be, a really long time before we can see the effects of it. So for humans or for mammals, they use mice and rats. For birds, sometimes they use pigeons. For fish, they use trout. So they use a variety of things to kind of blanket all mammals. So mice and rats are used for all mammals. And of course, it's going to be a little bit different. And when they figure out the lethal dose, they also play on the safe side. So they take 10% off of that amount. So if the lethal dose is 100 grams, they're going to drop that down to 90. So just to play it safe for humans. All right, so they can do two different studies. So let's say that we're doing a study on effective dose or lethal dose, or just the effects of something on a human. So we can't really look at the effective dose of a nuclear meltdown without that actually occurring. So sometimes we can't do a study until it actually happens. So a retrospective study would be just that. So something happens, a disaster, and we can look back and we can look at what happens to those people. So in Chernobyl, for example, what happened to the people that were exposed? What happened to the people that were exposed in a natural disaster like Fukushima? Or what happens to people in Flint, Michigan, for example. So those are retrospective. It happened. Now let's go back and look at what those people were like before, maybe their medical records, and then look at after. And then a prospective study would be people that might be exposed. So let's say that you have people near something that might occur. Maybe they're smokers, and so you want to look at their whole life, or not even their whole life, but just like a time period that they're smokers and they're diabetic, or something. So a prospective study would be it's ongoing, maybe before they're exposed, maybe during exposure or something like that. And then synergistic interactions. So this is something that it's really hard to predict. So how are things going to affect you if you've got multiple things going on? So let's say, for example, you are exposed to radon. So radon can cause lung cancer, but you're also a smoker. So a normal person being exposed to radon might have a, I don't know, 10% chance, there's three numbers out there, but 10% chance of developing lung cancer, which is, radon is pretty bad for lung cancer. But so you have a 10% chance. Well, let's say that you're a smoker. Well, instead of having that 10% chance, you have a 90% chance that you're going to develop lung cancer. So they can interact and cause you to have a greater risk because you're already, your lungs are already damaged, or something like that. So it's really hard to kind of judge this because the human body is so different. All right, so we need to understand where things are getting their um, chemicals or toxic chemicals in their body from. So we did bring this up a while back. You guys did a little simulation with mercury in a cup, and then you made it smaller and smaller and smaller. So that was biomagnification. So biomagnification was something that moves up the food chain is going to become more and more concentrated. And so that's what we were mimicking. We were mimicking mercury in the ecosystem, but in my example, I have DDT. So DDT can do the same thing. It can move up in the food chain and accumulate in a organism's body really dramatically through the food chain. And then bioaccumulation is different. Bioaccumulation is how does it get into your body, not through eating, so not through the food chain, but just exposure over time. So, for example, if you're exposed to mercury slowly over time, so you're not eating it. Let's say it's in your water and you're slowly drinking it. So it's going to accumulate. It's not going to leave your body ever. So it's going to accumulate very slowly over time. Or the hat makers, for example, that they mentioned, the Mad Hatter. So that's bioaccumulation. They weren't eating it. They were just exposed to it slowly over time and it accumulated in their body until it made them crazy. So that's accumulation. So just in one organism over a long period of time. Whereas biomagnification is moving up the food chain. So that's how they're different. And then this last thing here, this just shows the persistence. So persistence is important. How long does it stay in the ecosystem? So different chemicals here, and it gives what they are and their half-life. So that means how long does it take to break down in half? So if I start with 100 grams of a substance, it's going to, of this malathion, I'm not sure how to pronounce it, but its half-life is 1 day. So after a day, you have 50 grams. After 2 days, you have 25 grams. After 3 days, you have 12.5 grams. So it's going to break down pretty fast. Radon, 4 days in the air. And then you can see DDT, 30 years in the soil. So even though we stopped using DDT a long time ago, it's persistent in the environment. So it is still around. It'll be around for a while. And then you can see PCBs. These are, a lot of you guys talked about things like this with plastics. And so 8 to 15 years in the water, it's a pretty long time to persist in the water. So that can accumulate in organisms pretty quickly if it's going to stick around, or this for 30 years, that's going to accumulate quite a bit. So it'll be a long time for that to come out. So this is important to understand when we're using stuff. How long is it going to persist? And the longer it persists, the worse it is and the less we want to use it. So it needs to only be used if it's absolutely necessary. And that is it. So I hope you enjoyed, and I'll see you next time.